Suppose a user submits a strict enterprise query to an internal database. What was the Q3 revenue for Project Alpha? On this dark mode terminal UI, we see the system retrieve passages and display incredibly high similarity scores, like 0.92. But the actual text chunks returned are for Project Beta, or they reference Q2 instead of Q3. This highlights the mechanical limit of basic retrieval. A high similarity score proves that a text chunk is topically related to the prompt, but it does not guarantee a factual match for specific parameters. When a system prioritizes broad topical alignment over exact criteria, it feeds incorrect data to the language model. The model then generates a highly confident, factually wrong answer. Single-shot semantic retrieval lacks the precision required for complex professional queries. To return accurate data, the architecture must evolve. Standard bi-encoder RAG systems operate by mapping text strings into a mathematical space. Vectors for reset password and forgot login point to the same dense cluster in a 3D grid labeled off. They share the same conceptual space, but the vector for ERR4052 floats entirely isolated. Abstract meaning is irrelevant here, only the exact character sequence matters. Standard vector search relies purely on these spatial relationships and is entirely blind to exact syntax. Relying exclusively on spatial meaning creates a massive precision gap. Without a fallback mechanism for exact keyword matching, specific data retrieval fails. The primary architectural upgrade to fix this blind spot is hybrid search. We start by bringing in BM25. This is the algorithm behind traditional search engines, and it excels at finding exact character-for-character term matches. However, BM25 has a strict limitation. Because it looks for exact characters, it is completely blind to synonyms and paraphrasing. To get the benefits of both, we use the parallel architecture shown in this diagram. A single query splits into two streams, one routing through a vector database node for spatial meaning, and the other through a keyword index array for exact matches. This introduces an immediate engineering bottleneck. Vector similarity produces a spatial distance score, while BM25 produces a keyword frequency score. The two metrics are incompatible. If we cannot mathematically combine these vastly different scoring systems, the hybrid architecture stalls out. The solution is an algorithm called reciprocal rank fusion, or RRF. RRF discards raw scores entirely, applying a rank-based formula, 1 over k plus rank. A top result is exactly 1 over 61. K, set to 60, normalizes the curve. Subsequent scores become 1 over 62, 63, creating a smooth decay curve. For the final merge, the system sums rank scores from both vector and keyword streams. Documents performing well in both bubble to the top. RRF mathematically balances exactness with meaning, producing an objective boost in retrieval precision. Even with hybrid search functioning perfectly, a top 20 result list will still contain marginally relevant noise. The flaw lies in the first stage bi-encoders. The query and document vectors are computed separately, never directly interacting during retrieval. To isolate true relevance, we introduce cross-encoder re-ranking. This acts as a deep interaction filter. This diagram details the cross-encoder execution. A query text block and a candidate document block merge into a single transformer node simultaneously. Because the model processes both texts together, it outputs a highly precise single relevant score. The computational trade-off is speed. Cross-encoders are too slow for the entire database. They are restricted to evaluating only the top 50 results. By deploying cross-encoders as a secondary filter, engineers ensure only the most deeply contextualized documents ever reach the language model. Sometimes the database architecture is flawless, but the user interface receives a short, ambiguous query that breaks the pipeline. To fix the query itself, we use a counterintuitive transformation technique called hypothetical document embeddings, or HIDE. A user submits a short query, context overflow. HIDE immediately forces the language model to hallucinate a dense, multi-sentence answer. In a 3D vector space, this hallucinated paragraph maps directly onto a tight cluster of target source documents, providing far higher spatial overlap. HIDE upgrades retrieval by searching based on the anticipated shape of the answer, bypassing the structural limits of the original question. Upgrading an architecture requires a way to mathematically prove those upgrades are actually improving the output. The industry standard for evaluating these pipelines is the RAGAS framework. RAGAS splits evaluation into specific components. Faithfulness and answer relevancy strictly measure the generation quality of the language model itself. This radar chart plots the full evaluation. While the first two measure generation, context precision and context recall strictly measure the retrieval quality of the database. Automated LLM as judge frameworks like RAGAS are mandatory for catching pipeline regressions before deploying to production. The final evolution moves away from static, linear pipelines and toward dynamic, agentic systems. A mechanical sorting arm rejecting objects illustrates the core premise of agentic RAG. The system gains autonomy to evaluate its results and trigger corrective actions. One approach is self-RAG. It utilizes special inline reflection tokens generated during the inference phase. The tokens act as automated, real-time fact-checkers. The isRelevant token evaluates retrieved chunks, while the isSupported token flags any claim in the response that lacks evidential backing. By enforcing strict internal evidential thresholds, these reflection tokens prevent hallucinations at the millisecond of generation. For a complete self-governing workflow, systems deploy the corrective GRAG or CRAG pattern. In step 1, the plan phase, the agent takes a complex query like Project Alpha Q3 and decomposes it into smaller, discrete subtasks. Step 2 is retrieve. The master query splits into two executing nodes, find financial data and filter for Q3. Step 3 is critique. An LLM judge node inspects the streams, flashing a red isSupported false error on the Q3 path. The algorithm recognizes a failure. It pulled Project Alpha data, but lacks the Q3 modifier. This triggers step 4, re-retrieve. The agent loops a red pathway back to the start, rewrites its query, and executes a new search. This self-correction loop runs continuously until the strict evaluation threshold is explicitly met. The CRAG pattern transforms retrieval into an iterative sequence of lookup and critique, functioning like a specialized research loop rather than a static database query. High-precision data retrieval requires moving past blind vector lookups towards advanced filtering and autonomous research loops. This master architectural map displays the full pipeline. Hybrid search with reciprocal rank fusion and cross-encoders lock in data precision. HIDE aligns the query, and CRAG drives autonomous correction. Enterprise retrieval requires an architecture engineered to iteratively verify its own facts.